silhouette by the hot star. So now you can see it's a continuous jet. It does meander somewhat, and it may be that the jet process is precessing or somehow unstable in the way it points a little bit. But there's a star buried in there, and it's shooting a jet out this way, and also one this way, but of course you can't see that one. It's buried in there. But there it is. So that's the final angular momentum solution taking place there. Okay, that's enough for star formation. Let me move on now to what happens in that disk. So first of all, just to reiterate, if we look at our own solar system, we see lots of interesting features to it. The planets are all orbiting in essentially the same plane. That's what gives rise to the zodiac. The zodiac is the plane of our disk, cut into the sky. And all the planets travel along. Okay? They all go in the same direction, too. So the disk is all rotating, and they're all going the same way. So they were all embedded in this one plane which rotated in one way. The orbits are fairly circular in that. Also, the moons orbit in the same direction. Then there's another kind of regularity, which is the inner planets are relatively small and basically rocky. We're standing on one of those. But the outer planets are relatively larger and mostly gaseous. And finally, the spacing of the planets are somewhat regular. And I have to tell you right now, we have no clue why that is. It probably means something, but nobody knows what it means. But the basic implications of these facts of the solar system are that it must have formed in a single flattened rotating system, a disk, around our sun. And the other thing you might take away is that the distance from the sun mattered in the formation of the planets. The inner ones were rocky, the outer ones were gaseous. And we can then ask, okay, now I see all these disks around other stars. Do they have enough mass to make systems like ours? And are they probably doing that? Well, here's a answer to the first part of the question. This is a plot of how many disks we see that have given mass. And this is in solar masses, so this would be a disk that has the same mass as our sun. We don't see any of those. Okay, we see some that have a few tenths of our sun's mass, and then lots of them that are in here. This line right here is how massive we think the disk that made our solar system was. So if you take the planets and you remember that there used to be a lot of gas that went along with that dust, you add that back in, and you ask how much mass was there total. It was about 1% the mass of our sun. So that's here. Most of these disks have more mass than that. So apparently there's no lack of material to build a solar system similar to ours in the typical star forms. That's promising. And in fact, we can even see in some cases that it's there. Here are a couple of Hubble pictures of older stars. Now these are not forming anymore. I guess I didn't say. These disks are there when the stars are forming, and then we can see them for about 10 million years. And then they vanish. And we're not quite sure why. The way that we see them, as you saw, is with dust. And it's micron-sized dust particles. And if the dust would coagulate, for example, into marbles, we wouldn't see it anymore. That's one way they could disappear. Another way, of course, is they could accrete onto the star and no disk, or the star might blow them away too. So we actually don't know what destroys the disks, but they are gone after about 10 million years. They might be gone because they've started making planets, so that doesn't necessarily mean anything. But here are some older stars, and this is reflected light on dust. You can see there's a disk around this star. There's a disk around this one. In fact, it looks like a ring. We don't know of any way to convert a disk to a ring except by putting some kind of body in there to disturb it. So this might be evidence for a planet orbiting inside here. We don't know. But for sure there's dust there, and it has this ring-like character. Yeah? Yeah, the X is an artifact of the telescope. Okay. Yeah. And this is the size of our own solar system in this picture, and here also, the diameter of Neptune's orbit, just for scale. So these are actually substantially bigger than Neptune's orbit. We actually think our own solar system is substantially bigger than Neptune's orbit as well. Our disk formed planets out to Neptune, but it extended much beyond that. And it's the so-called Kuiper belt of objects, of which Pluto is the prime example. But in fact, there must be objects which extend out to twice Pluto's orbit. And we're beginning to find them just in the last 5 years or so. So the remains of our own disk are still out there, and the true size of our solar system is at least twice Pluto's orbit, comparable to these things. So this is the basic picture that we have of the formation of our own solar system, but as you can already appreciate, this is probably the general picture. You have the star, and it's surrounded by this huge disk of gas and dust. Okay, it's about 100 times as much gas as dust originally. But the dust begins to coagulate, and in the inner part of the disk, it's hot. So only things which can condense, when it's hot, will condense. Well, what's that? Rock condenses a lot more easily than ice condenses, right? So I can melt ice, but I can have rock not melting. So that's basically what goes on in the inside. At some point, though, it gets cold enough that ice can not melt either. That's actually at about the distance of Jupiter. And there, you can get water ice, and then ammonia ice, and methane ice. And those are much more common elements. And those involve hydrogen with oxygen, carbon, and nitrogen. All that's much more common than, say, silicon and magnesium, the things that rocks are made of. So there's far more icy material out here than there is rocky material in here. And so maybe that explains the basic fact that the inner planets are small and rocky, and the outer planets are large and gaseous. It's a little more complicated than that. Of course, we have to take this micron-sized dust and convert it into the Earth. And to be honest, that conversion process isn't very well understood either. This is the part where we wave our hands. So you start off with these dust grains that are very tiny, and so these dust grains clump into planetesimals. So we have these micron-sized things, and we get kilometer-sized rocks out of them. How that happens, we don't know. The problem is that if you have sand, let's say, and you try to make sandballs out of it, it doesn't work very well. Snow, on the other hand, works quite well for making balls, right? So it's easier to understand how you might clump icy things together to make big bodies than it is to understand how you get rocky bodies that are a kilometer across. And so stay tuned. People are working on it, but we don't know the answer to that. We do know, though, that it happens, because we can see them in our solar system. The basic building block for the planets was these sort of kilometer-sized objects. And we see them around today. This is what they look like. They're comets. Those are icy planetesimals. The typical comet has an icy rock nucleus. It's rock mixed with ice, 1 to 10 kilometers in diameter. The stuff you see is just the ice evaporating off as it comes near the sun. So that's huge, but actually all there is in there is this tiny little 5-kilometer ice ball. But there are billions of those in orbit around our sun. So we know for sure that there were a huge number of sort of 1 to 10 kilometer sized bodies that must have come together to make the planets. And once you can make planetesimals, the rest of the process is pretty straightforward. And because the composition of the solar nebula changes from the inside to the outside, that would also explain why the planets look different from the inside to the outside. So let me talk just a bit more about some formation processes for the planets. So the one I've been saying so far is the main one that we've thought about, which is basically agglomeration of planetesimals. So given the kilometer-sized bodies, what happens is the rich get richer. As you start putting a few of them together, there's a little extra gravity there compared with smaller things. Has a little extra and a little extra cross-section. So it's a little better at grabbing more. But of course, the more it grabs, the better it gets. So there's a positive feedback mechanism whereby a few of the lucky planetesimals that start off a little bigger will grow bigger more fast than anybody else, and eventually become large bodies. And once they're large bodies, of course, they can collect lots of planetesimals. They're much bigger than that. And whether those things that come in are ice or rock kind of determines what kind of body you're going to get out of this. Okay? So in the end, you'll get a rocky or icy body that's sort of 1/10 to 10 times the mass of the Earth. And that's the sort of main way people think about this. And that must have been the process for the terrestrial planets, and also probably for some of the moons of the planets that are big, and so on. But then there's something else, obviously, that happens. This is just like economics as well. So if you're really rich, then you're in a very good position to make way more money. So once you get a 10 to 15 Earth mass core, it's actually so powerful, it can begin to suck gas directly from the nebula. It doesn't have to rely on planetesimals anymore. It will just suck hydrogen and helium straight from the nebula. And so once you reach that size, you get a runaway accretion process where gas itself just streams onto the object and is captured. And that's how you make a gas giant. The thing that could stop that is eventually you'll sort of take all the gas that's available in your orbit and kind of open up a gap in the disk. And people thought that sort of limited the size to about 1 Jupiter. That would open enough of the gap to sort of shut this off. We now understand that it's still possible for gas to sort of get through in little streams. You might be able to build up several Jupiter masses that way. Okay? And in fact, we see several Jupiter mass objects around other stars. So that's the sort of gas giant planet model. Lately, in the last couple of years, a third process has become kind of serious, and I assure you that it will be thought of even more seriously in the years to come, and that is the possibility that we could forget about this whole planetesimal thing altogether and get direct gravitational instabilities right in the disk. Like maybe in a spiral arm, you get spiral shocks, and people have some models that sort of work. And enough gas gets compressed enough to make a gas giant directly. You don't build up the rock ice core and suck gas in. You just get collapse within the disk. And then there's not so much of a limit on how big an object you can make. So you might be able to make 10, 15, 20 Jupiter mass objects that way. Now, in fact, Jupiter itself is not completely clear that it formed this way. I mean, people always thought that. Galileo spacecraft has been orbiting Jupiter for several years now, and they've got a very careful measurement of the internal structure of Jupiter. They don't see a rock ice core like they expected. The limit on it is now down to 5 Earth masses. And it's not completely clear that Jupiter formed that way. It might have formed that way. That would be very interesting. But I'll just leave that as speculation for the moment. And I think I'm just about out of time, so I will finish by saying that what I hope you've gotten are sort of 3 things. 1, stars are forming all the time in our galaxy today. 2, when they form, they typically form with conditions that are conducive to planet formation. And 3, we've now begun to discover that indeed many stars have planets around them, other stars. Of the stars that have been surveyed for planets, something like 5% already show planets. And our survey techniques are very crude. We can only find high mass planets very close to the star. We would miss our own solar system still. So it's already up to 5%. And as we get better, I think you can expect the number of stars which are known to have planets around them to increase to, I don't know, maybe as high as 30 or 40%. Which means that a lot of stars in our galaxy have planets, and that the process of planet formation is kind of part and parcel of the process of star formation. And I'll end there. Somebody will need to turn the lights on before I turn it off. Oh, sure. Yeah.
The model that you showed for having small rocky planets close to the star and the gas giants to be far away is based on one example of home solar system.
That's right.
And it seems that all of the examples that we have of other solar systems, we have gas giants very close into the star. And I understand that is an artifact of the primitive methods we were using to wallow in the star. But what are your thoughts about how a gas giant could exist so close to a star?
Right. I would have gotten to that if I had more time, because that's an important point. So what he said was that what we actually found so far is two violations of what I said our solar system tells us about planet formation. One, the gas giants are inside the ice boundary, where you would expect rocky planetesimals to exist. And two, they're not in circular orbits either. They're all in eccentric orbits, compared with the circular orbits in our own solar system. Now, there are two possibilities, well, probably three possibilities for why that is. As you pointed out correctly, you shouldn't think that most solar systems are like that either, because our observational techniques are very biased to finding inner giant planets. So the fact that we found 5%, could be interpreted as meaning that 95% of solar systems are like ours, and we can't see them yet. But we don't know that either. We just haven't seen anything. But how do we do at least have 5% that do look weird compared to our solar system. And there's sort of three thoughts on that. One is that the gas giants did form outside the ice boundary, like we think they should have. Then the disk, remember, was dumping angular momentum. It's still accreting. And the planet opens up a tidal gap in the disk. But if the disk is still accreting, it's basically going to drag the planet with it due to these tidal interactions. So one possibility is the giant planets do form where they're supposed to, according to theory, and then they get dragged into close to the star by the disk. That's one possibility. That wouldn't explain why they're eccentric, though. You kind of think they'd be in circular orbits then. Another possibility is that it looks like it's easier than we thought to make gas giants. And so if you make several of them, then if they're too close to each other, they really have chaotic orbits. And what typically happens is one or more of the planets is actually ejected out of the system altogether. And it takes a bunch of angular momentum with it. So the ones that are left drop in towards the star and usually end up in an eccentric orbit. So that's probably the favored explanation at the moment, would be that these systems form several giant planets. We're seeing the inner one. There was probably one that was thrown out, and there might be one out there still somewhere. That's a possibility. The third possibility is the third one that I gave here, which is that giant planets actually form directly by gravitational collapse, and we don't care about the ice boundaries or anything. There's just a portion of the disk that collapses into a giant planet, and that could happen in principle inward of the ice boundary. We don't know what kind of orbit you'd expect in that case. That's more speculative, but that's another possibility. So I think the lesson to be drawn so far is we don't really know how planets are made, especially giant planets. It's just that there are apparently quite a lot of them, and the story is more interesting than our solar system implied. I should maybe also point out that all those systems where a giant planet's been found so far couldn't possibly have Earth-like planets in them because the giant planet is roving in an eccentric orbit in the inner solar system, and it would certainly throw any terrestrial planets out of there. So there can't be any Earths in those systems. So those aren't the place to look for. You shouldn't do search for artificial intelligence on any of the systems where we found a planet. You should go to the other ones. Yeah.
Do most stars form in clusters? Do we have any idea about that?
Yeah, I skipped that as well in the interest of time. Let me back up a bit. So this is what I would have said. There are two important wrinkles on the sort of picture that I gave you, one of which is the environment in which the star forms. So you have this molecular cloud. What I did with my laser pointer. There it is. You have this molecular cloud, and in the case of a cloud like Orion, it forms a lot of stars. You have 100,000 solar masses there, and if it makes high mass stars, it can't do that unless it's really quite dense. And if it's really quite dense, lots and lots of low mass stars form. So in fact, here is a picture of the Orion Nebula again, but now taken in the infrared. We can't see it very well, but let's not turn the lights off. So here's the Orion Nebula. All these other dots here are low mass stars that are hidden behind the dust, but you can see in the infrared. There are about 3,000 stars forming in that trapezium region. And if you go around counting up, how many giant molecular clouds like this are there versus other kinds of clouds, you can reach the conclusion that this is where the typical star comes from. So yes, I think clustering is very important. It's not clear, even in this case, whether that cluster is going to stay together or not. Because what happens is all that gas is what is holding it together. As I said, most of that doesn't form stars. If enough of it doesn't form stars, but is blown away, then there's not enough gravity to hold the thing together anymore. All the stars will disperse into the field. So probably that's the source of most of the stars in the field. They formed in a giant molecular complex which didn't stay bound, and they scattered out to the four winds. So yes, I think that's very important. The other wrinkle that I didn't make much of, but is worth mentioning, is that the average star has a companion to it. Our sun is atypical in that respect as well. Usually what happens is you get a couple of stars, and they each have a disk around them, and then there's a disk around the binary as well. That's more common than a single star forming by itself. And then whether you're going to get planets or not just depends on this separation here. The median separation of the two stars like this is about twice the orbit of Pluto, 88 meters. So you could have inner planets around both stars in that case, and they'd be in stable orbits. So at least half the binary stars are positioned to have planets around two stars. If you bring them too close, then of course there aren't stable planetary orbits, but it's like 10% or 15% of binaries where you really don't expect any planets at all. Yeah. No, I didn't say anything about that. That's a whole different story. That's the story of the lives of stars. But so I'll just cut it real short by saying all the heavy elements are cooked up in the interiors of stars. And then to get them back into the interstellar medium to make dust, which makes planets, you have to do one of two things. The low mass stars like the sun kind of gently waft them back into the interstellar medium at the end of their lives, some of the material. The sun, for example, when it dies, about 40% of its outer atmosphere will be returned to the interstellar medium. And before that happens, it will mix some of the nuclear products up from the core. That gets you elements out to iron or so. The only source of all the elements heavier than iron is supernova explosions. So I also didn't mention this, well, it's sort of pictured here. The high mass star that was shredding its neighborhood isn't even started yet. It's only going to live for 3 million years these high mass stars have very short lifetimes. So while the cloud is still present, and while other stars are kind of getting it together, this star is going to run out of fuel and explode in a tremendously violent explosion. And that'll really shred the neighborhood nicely. But in the process of the explosion, all the elements heavier than iron are both produced and spewed into the interstellar medium. So that's the source of the other elements. So very early in our galaxy, before much of that had happened, there was really only hydrogen and helium around. But now we've gone through many generations of high mass stars, and we're as contaminated as we are with heavy elements. Yeah.
You commented a little bit about Pluto. I wonder if you could say a little more about why it seems to violate most of those regularities you mentioned.
Well, because there was a big public brouhaha last year about whether Pluto's really a planet or not. That's a semantic argument. It's not a regular planet in the sense of being in the orbital plane of the disk and so on. It's one of these. It's a heavy example of a planetesimal in the rest of the disk, and its orbit's been perturbed out of the plane of the disk. It's tilted at sort of 20 degrees or so, and we see that the Kuiper belt objects, some of them are perturbed in orbits just like that. So there are literally billions of other objects out beyond Pluto. Maybe not so many that are as massive as it is, but lots of them that are reasonably massive. And they're spread out, probably out to 100 AU or so. And some of them are in kind of cockamamie orbits. But the disk is sort of generally still there. Outside of that, there's what's the so-called Oort cloud of comets, which of course are just icy planetesimals. Those are planetesimals which were in the solar system, which came near Jupiter and were really tossed up. So they're spread sort of in a sphere around the sun, and that's got a radius of 100,000 AU or 200,000 AU. And we also think there are billions of those out there. So Pluto is in with one class of planetesimals that are sort of still in the plane of the disk somewhat. And then there's another class which are sprayed all over the place that give you the long period comets. So that's why Pluto is in a funny orbit. Now, whether you want to call it a planet or not, that's up to you. One last question?
Let's thank Dr.